Welcome! In this video I will show you how to solve problem 6.30 as it appears in the third edition of Griffiths Introduction to Quantum Mechanics. Now in this problem there are three parts to the question. First of all, we are asked to plug s equals 0, 1, 2 and 3 into Kramer's relation. Then we are asked to plug in s equal to -1 and to see what happens. And finally, determine the expectation value of r to the -3. Why is that important? That is important because that is actually the value that we need when we are dealing with the spin orbit Hamiltonian. You might have seen that we already did a video on it, and there we ended up still needing the value of the expectation value of r to the -3. So here we are finally going to show it. Okay, so recall Kramer's relation. It is what I wrote down here. And, well, it's actually quite a straightforward problem. So we literally just have to plug in s equals 0, 1, 2, and 3 and do a little bit of algebra. So let's begin. S equals 0. Well, this s is 0, so we get 1 over n squared r to the 0th power. So that is the expectation value of 1, which is simply going to be 1, right? Because the expectation value is this integral, it's normalized, so you simply get 1 out of it. Then we have minus 2 times 0, so 0 plus 1, so we get minus a times r to the -1, and then we have a plus s over 4. That is simply 0, so we get plus 0 equal 0. Okay, so here quite simply we can now leave this 1 over n squared here, and this is equal to a expectation value of r to the -1. And well, and this part is then already done. We simply have to find this expectation value, so we get, maybe write it like this, expectation value of 1 over r. This is going to be 1 over n squared a. All right, pretty cool. So, you know, that's the first part. So using s equals 0 allows us to find the expectation value of 1 over r. Now let's take the Kramer's relation and go to the next page to plug in s equal to 1. So s equal to 1. So in that case here we have 2 over n squared times expectation value of r minus, and here we have 2 plus 1, so we get minus 3a, expectation value of, and this time it's r to the 0 here, so this part is now going to be 1, this, and then we get plus 1 over 4 times, then we have 2l plus 1 squared minus 1, and times a squared, and there expectation value of r to the first power, or to the minus first power, sorry. So this is r to the -1, but we already found that value, right? We literally just found it. So let's plug it in, and that is going to be 1 over n squared a. Okay, let me double check. I don't want to make a dumb mistake. There, yeah. Okay, and this is equal to 0. Amazing. So let's just take a quick look. What is it that we have to solve for? Well, the expectation value of r here is the only unknown, because in principle both n and l is something we should know, right? They are the quantum numbers, so if we are given or we want to look for a certain state, we can just plug them into this equation. A is a constant, so yeah, this is the only thing we have to solve for. So let's do that. Let's leave this on the left hand side, so we get 2 over n squared expectation value of r, and this is going to be equal to, and let's put everything to the right hand side. So we get plus 3a from this, minus 1/4, and let's expand whatever is in here. So we get 4l squared plus 4l plus 1 minus 1. All right, so the ones will cancel out, and we have 1/4 and these 4s, so maybe let's just cancel them. And we can actually factor this out as well, right? This is simply l times l plus 1. So let's write it like that. So this big thing is now simply l times l plus 1. And let's get rid of this. And of course, there is still an a squared multiplying it, a squared. and this is divided by n squared a, so I guess the a squared will simply be, what was that? The a squared will now simply be a, and we have to divide by n squared. Okay, now great, we just have to finish this up. So let's see, we get expectation value of r. This is equal to, and we can now factor out an a if we want, so maybe leave it as a times, let's see, a over 2, right, because we have to divide by this 2 right here, and then we get n squared times 3n squared. This n squared will be cancelled out by this one, and this a is already outside, so we get minus L, wait, is it minus? Yeah, it is minus. All right, so that is the expectation value of R. I'm gonna put a little box around it because we will certainly need it later. And I'll also write the expectation value of R to the to the minus 1 because that's gonna come back soon. All right, great. So that's s equals 0 and s equal to 1. Let's now go to s equal 2. So s equal 2. So let's plug it in. Here we get 3 over n squared r to the second power minus, and here we get 4 plus 1, so that's 5a r to the, and this time we get 1 here plus 2 over 4, which is 1/2. And here let's multiply through again, so we get 4l times l plus 1, and then we get plus 1 minus 4, so we get minus 3. So minus 3. All right, what else? So then we have a squared and r s minus 2, but if s is 2, then this here is expectation value of 1, which is again 1. Okay, great. So now the expectation value of r to the first power is what we just found. That is a over 2. So maybe let's plug it in next. So 3n squared r squared. And now let's put everything to the right hand side and plug in the expectation value. So we get 5a times a over 2, I believe it was, 3n squared minus l plus 1, probably, right? Yeah, yes, that's it. Okay, and that's the first part. What else? Then we have this. So minus a squared over 2 times 4l l plus 1 minus 3. All right, so we can do a few things. So we have a here and a here, so maybe let's combine them and also put the divided by 2 outside. So we get 5 over 2 a squared. And now if you notice, we can factor out a few more things. So we get a squared over 2 factor of all of this. And so let's multiply through by the 5. So we get 15 n squared minus 5 l plus 1. And then we have this. So there we get minus 4 l plus 1 plus 3. Right, so yeah, so we can combine these two to get minus 9. So we get minus 9 l plus 1 plus 3. I'm just gonna move it a little bit. And now we simply have to divide through by this. So, and actually we have a 3 here, so we can divide both sides by a 3 since everything is a multiple of 3. So this will be just 1 here. This 15 will be 5. This 9 will be 3. Oh my god, my tablet is lagging. There we go. and this 3 is 1. All right, so let's now multiply by n squared. So our final result, the expectation value of r squared will be a squared n squared divided by 2 times 5n squared minus 3l l plus 1 plus 1. All right, so that's another result. Great. Now let's do this one more time for s equal 3. So what we are seeing here is that every time we plug in s equal to something, we get a nice formula that is actually quite easy to solve for the expectation value of r. That would be a very annoying integral if we, didn't have this. But the Kramer's relation makes it very easy as long as we have the information of other expectation values. So let's see our final case, which is s equal 3. So if we plug in s equal 3, we get 4 over n squared, expectation value of r cubed, minus 7a, expectation value of r squared, plus 3 over 4, 4l, l plus 1, and then we get plus 1 minus 9, right? Yes, because s is 3. So this would be minus 8. So minus 8, a squared, expectation value of r to the first power. Okay, so as we can see, this is a recursive formula. And in order to find the highest value, so expectation value of r cubed, we need to know beforehand the expectation values of r squared and of r. If we don't have that, then this is useless, okay? All right, so let's plug them in because we actually do have them. So we do know the expectation value of r squared and of r. We have just found them. So 4 over n squared, r cubed, this is equal to. So this will be 7a times what we just found, which I already forgot, which is a squared n squared over probably 2, I think. Yeah. And then 5n squared minus 3l, l plus 1, plus 1. All right. So that is the first part, right? I didn't forget anything else? No. Okay. So that's this. And then we get all of this other beast. Maybe change color to make it look different. So we get minus 3 over 4, 4l, l plus 1 minus 8, a squared times the expectation value of r, which is somewhere up here, which is a over 2, so times a over 2, times 3n squared minus l plus 1. Or was it something multiplying it? No, that's it. Okay. I don't have much room left, so I'll just take this to the next page. All right. Oh, the 4 is not quite on screen. All right. So now we just have to multiply through a little bit. As I mentioned, this is not really difficult, but it does involve a lot of algebra. Okay, so here we get 7 over 2 a cubed n squared. And, well, I guess we could multiply through here. But maybe let's see what this part has in store first, so we can see what it is that we need. So 5n squared minus 3l, l plus 1 plus 1. So let's for now just leave it hanging, right? Yeah. Okay, so what do we have here? Here we get minus 3a cubed divided by 8. All right, so combining these with these. And then we get the product of these two brackets. So we get 12n squared l plus 1. And then we get this times this. So we get minus 4L squared L plus 1 squared. Let's continue down here because I don't have much more room. Then we get minus 24n squared, and then plus 8L L plus 1. Okay, so let's compare these two things. So both of them are multiplied by a cubed, and some of them will have n squares, some won't. There is this 4 down up there, which we might use, but I guess I'll use it later. Oh, what we can do, by the way, we have this 8 here, and all of these are multiples of 4, so we can actually simplify. So divide by 4 here, or basically take this and divide, right? So we get 2 here, and this will be divided by 4, so that's 3. And this here will be divided by 4, so we get 1. And that's a weird L. This is divided by 4, so that's a 6. And this is divided by 4, so that's a 2. All right. So yeah, let's now factor all of this out. So expectation value of r cubed. This is going to be. So let's factor out a cubed, and that's it. And well, and divided by 2. So I'm going to multiply through by 7. So we get, and by n squared. So we get 35n to the 4th power minus, now 7 times 3, so minus 21n squared L plus 1 plus 7n squared. And now let's go here. So this a cubed is already here. This divided by 2 is already here. So we have to multiply through by minus 3. So we get minus 9n squared L plus 1 from this part. Then we get plus 3 L squared L plus 1 squared from this. And then we have plus 18n squared from this. And finally minus 6 L plus 1. So now I will copy this, take it to the next page so we can work it out in peace and quiet. Okay, so I brought some things along that I didn't mean to. Okay, so let's see. The left hand side is still the same, nothing new there. All right, so a cubed divided by 2. So we have nothing to simplify this with, so let's just keep it. Then we have terms of n squared L plus 1. So we have 1 here and 1 here. So we get minus 30 n squared L plus 1. Then we have this and this. So plus 25 n squared. And finally we have... actually, we can't combine them, so we can't. Okay, so L minus 6L L plus 1 and plus 3L squared L plus 1 squared. Oh, well, I guess we're not quite done. We still need to multiply through by n squared and divide by 4. So we would get n squared and divide by 4. There we go. Amazing. So it doesn't look particularly pretty, but this is a formula for the expectation value of r cubed. And you can imagine if the end result looks this bad, calculating this by traditional methods must be very, very, very annoying. So I'm glad that we didn't have to. So this is the way to use Kramer's relation. Now let's go to part B, because in part B they say let's plug in s equal minus 1 to Kramer's relation and see what happens. So let's do exactly that. Let's go back here. And maybe I shouldn't have deleted. I'm going to write it here. So expectation value of 1 over r is 1 over n squared a, just in case it pops up. I don't know if it's gonna, but okay. So let's plug in s equal minus 1. So if we do that, this part is going to be 0, right? So minus 1 plus 1, 0. So this part does nothing. Then we get minus 1 here. So this is minus 2 plus 1 minus 1. So this minus turns into a plus. And we get a times the expectation value of minus 2. And then minus 1 over 4 times, well, the same as always. So 4L, L plus 1. And this is going to be minus 1 anyways, because the minus sign cancels out. And there's a plus 1 here, so that cancels out. And this 4 here is going to cancel out this right here. And then we get a squared times the expectation value of r to the minus 3. So if we plug in s equals 1, we get this. And what is this? This basically tells us if we have the expectation value of r to the minus 2, we can find the expectation value of r to the minus 3. But unlike what we had before, right, because when we started off with s equals 0, we immediately found the first expectation value, and then we could just keep going. But if we go to s equal minus 1, we need the expectation value of r minus 2, which we don't have, at least not by using Kramer's relation. So we have a little bit of a hiccup here. Right, so to use this, we need to know this expectation value, and we have to find it through some other means. We can't just find it with Kramer's relation itself. Fortunately, we already found it in a previous video when we used the Feynman-Hellman theorem. There we found the expectation value of r to the minus 2. So we can use it, okay? And it's actually right here. This is what we found previously. So let's just plug it in here. So plugging it in, we get a divided by L plus 1/2 n cubed a squared. This is equal to, and then we get L plus 1 a squared expectation value of r to the minus 3. So we can extremely quickly just find the expectation value. So the expectation value of r to the minus 3 is going to be, well, one of these a's will cancel out. So we get 1 over L plus 1/2, L plus 1, and then we get a cubed, n cubed. And there we go. That's it. And this is what we then have to plug into the Hamiltonian for the spin-orbit coupling. But as you can see, Kramer's relation is an extremely valuable tool to use because, you know, it can be really annoying to find these expectation values if we use, you know, just the traditional methods. So both the Feynman-Hellman theorem and the Kramer relation is honestly a really big help. And well, this problem was quite straightforward. All we did was literally just plug everything in, and yeah, that was it. So if there's any question, make sure to, you know, write them down in the comment section. I'm always checking them out. And if you like this, please leave a comment, share the video with your classmates. I really hope that this was useful. And of course, subscribe to the channel if you haven't already. It doesn't really cost anything to you, but it really helps me out a lot. So I'll see you in the next video. Thank you very much for watching.